topic this week is demand response. Demand response is about manipulating the consumptions. Last week we saw essentially how to manipulate or control the generation. In a smart grid we can control the generation, but also jointly the consumption. The mathematical technique to do this is model predictive control, which is the topic of today. And next week we will see how we use model predictive control to do demand response. The good news is that the bad thing was last week, so the hard part is optimization, and model predictive control is just using what we know of optimization. So we should be more relaxed this week and even more next week. Model predictive control is a very widespread technique in engineering, in energy systems in particular, and certainly in electrical grids, which consists in using optimization with a receding horizon, we will explain that in a few minutes, in order to get a controlled policy. We have already seen a policy last week when we talked about affine policies that were reacting to disturbance. A policy is in the context of a dynamic system which has this form. So this form here is, last week we had no concept of time essentially, except one or two parts in the lab, but essentially the state that we had last week was the result of two agents playing, us choosing a control, u, and nature or disturbance or things we don't control playing a disturbance d, and the result was a function of u and d. But now in reality, when we have dynamic systems that evolve over time, we have the current state plus the disturbance and the control that influence the next state. So we can capture all the systems we are trying to control with this equation. So it's important to understand the model in which context we are. That's the most important step to do. So we assume that at every time t, we observe the state xt of the system, and we choose one control action u. Then nature chooses a disturbance, and the state becomes x of t plus 1, given by this function. So the function f is assumed to be known. That's how we call modeling the plant, when the plant is in the context of when you're controlling a factory or a chemical reactor or a car, an autonomous car, or a smart grid. That's the equation of the grid that we know from the previous modules. And then, since we talk of optimization, we pay a cost that depends on the action we took, of the state we are, and that may be time varying. So the state we are is typically playing a role in the action because we want to bring the state somewhere. For example, the state of a grid needs to be such that the currents are not too large on the lines and the voltage is within the bounds. So if the resulting state of the grid is close to one of the bounds, we will put that as a penalty function here. And in the context of model predictive control, our goal is to minimize the integral of the cost over some period of time. Let's dive into an example that we will use recurrently in this module. This is an example. Now we leave a bit the grid and we talk only about controlling a load, which is a heating system for a house. Exactly this house. This house is David McKay's house. David was a university professor in Oxford, and he's very famous for a number of things. In particular, this one, a book, Renewable Energy Without the Hot Air, which is a book that he wrote and is freely available online. If you're interested in renewable energy and you don't know of this book, then it's time to repair this omission and get it. It's free. And it's a very, very simple book that contains essentially 2 to 5 page chapters on a given topic. For example, one of the topics is how to model the heating of a house. And this is contained in this book. Plus a lot of other topics, and it's indispensable resource for anybody interested in renewable energy. Unfortunately, David McKay passed away 2 years ago. So let's assume that we want to control a house like this one, and we have a heat pump, so it's controlled by electricity, and the prices of electricity are variable. Why are they variable? Well, that's one of the things that people want to do in smart grids, to influence the consumption by changing the prices. That's one way of influencing the consumption. But there are other reasons why prices might be variable. It could be, for example, that you have solar panels. And when you have solar panels, the electricity you get from the solar panels is essentially free. Whereas if you buy it from the main grid, it is at a different price. And the problem is to schedule the energy consumption taking into account the variable price. So how do we do that? Well, essentially, the idea is when the price is low, we would like to heat as much as possible. Not too much, of course, because that would be inefficient and perhaps too warm inside the house. If we need to open the windows because we heat too much, that's defeating the purpose of what we're doing. So we assume there is a comfort zone. The room temperature doesn't have to be exactly certain set value, but can be within a range. So that's the idea. The idea is you have a house, or in general a thermal load, which we can view as a big buffer of heat. And if we heat it when the electricity is very inexpensive, then it will be less expensive. Assuming it's fairly well insulated, because of course when we heat it in the night and we need the heat in the day, then some of the heat will dissipate. This is very classically done today in practically all of Switzerland for boilers. If you have an electric boiler, prices of electricity in many regions or by many DSOs is smaller at night. So you charge your boiler with hot water at night, and in many systems it's a very primitive system where we don't use MPC, but simply at night you heat the boiler at maximum temperature, and then during the rest of the day you don't heat the water anymore. So if you take 5 showers in a co-lock, the 5th guy might have cold water. That's the, I would say, the static way. What we want to do it is in a more sophisticated way. So for this, we need a dynamical equation. That's the equation F that says, based on my control action, what happens to my system. So what is my system? Well, my system, the state that I'm interested in is the temperature. I call T of T the temperature. I'm doing here a very simple model where I assume there's only one temperature. In reality, things are never as easy, and in the lab we will use a more realistic building model where there will be multiple temperature sensors. But here, to simplify, I assume there's only one temperature, so assume a very small homogeneous house. The disturbance is the outside temperature. If it's very hot, if it's warm outside, the house will leak less heat. To have a concrete and more accurate model, we will need to model also irradiation. If we have a sunny day, then the sun will heat the house for free, so that will also be a disturbance. It's a good disturbance in that case. The heating comes for free, so we don't need, if we know that it will be receiving a lot of heat tomorrow, perhaps we don't need to heat as much during the night when electricity is cheap. So those are the kind of things we will need to do. In this very simple example, I assume, like on this figure, that there is no sunshine in a standard UK winter day. So we can leave it, but of course in reality we would need to have it. So the state is the internal temperature, the disturbance is the outside temperature, and our control is the heat. We turn on the heat pump if it's a flexible heat pump, and we consume some amount of electricity, U of t. I'm assuming here discrete time system. We could write all of this in continuous time, but then it becomes very, very sophisticated mathematically. So I think we have enough mathematical sophistication so we can stay in discrete time. Though here I'm writing it in continuous time, right, dt. U of t is how much electricity I'm consuming, so I'm buying on my electricity bill. how much of this electricity translates into heat is given by this coefficient epsilon. Where's my pointer? Here, epsilon, which is called the coefficient of efficiency. If we have a resistive heater, like we have in old-style boilers, this is very close to 100% because it's very efficient to translate electricity into heat. If we have a heat pump, it can be larger than 100% because that's the principle of a thermodynamical system. The heat pump is extracting heat from somewhere, is using electricity for the transfer. So this can be, if it's a very efficient heat pump, it can be 2 to 3. If it's an inefficient one, it will be 1 dot something. So that's the coefficient of efficiency here. If you're using an old-style system with a resistance and a fan, then here epsilon will be a bit less than 1, but close to 1. And then there is time evolution, that is saying that, which is given here by this dt and d capital T. So capital T is the inside temperature, which is saying that what are the phenomena that occur? Well, I put some heat into the system, and this heat, modified by epsilon, will be used for 2 things. One is for increasing the room temperature by a coefficient that has to do with the inertia, depending on how thick the walls are. In David's house, the walls are not very thick. They are brick walls. If you have a Vaudoise type of house with very thick stone walls, then the coefficient, the inertia will be much larger, so the C will be much smaller. So some of the heat you're using goes into heating the air and the walls and all the things that are inside the house. And another part of it goes away, except if the house would be perfectly insulated, then this would be 0. But in reality, that's never the case. So part of it goes away, and it goes away in this simple model proportionally to the temperature difference between inside and outside. If it's warmer outside, some of the heat gets inside. The house is being heated by the outside air. In the UK in winter, it's unlikely, so it's probably the opposite. Some of the heat you put gets into the outside, so you're heating the country. That's the model. Now we will translate it into discrete time to make it tractable. And in discrete time, this is what we obtain. So this is the equation we had just a minute ago. I replace dt by delta t and d capital T by t plus 1 minus tt. So that's the temperature now and the temperature that will result of my control actions. So that's the equation, the capital F function of my system, which in compact form I write in this form. So that if during a short period of time, let's say period of 1 minute, if I choose to heat, that's the set point of the heat pump ut, then the resulting temperature in 1 minute will be given by this. It's a linear function of the actual temperature now, of how much heat I put into the system. Of course, alpha is positive, and a coefficient that has to do with the outside temperature. So this is the system model. We need also to give a cost. So here in this case, I'm doing something that involves 2 parts. The first part of the cost is, of course, how much I pay. So P sub T is the price of energy. UT is the electricity I'm buying from the grid. So this is how much I pay. And that could be it. I could add constraints, but it's very convenient to replace hard constraints by what is called soft constraints, by putting a cost associated with the violation of the constraint we have. So the constraint we have on the state here is that the temperature should be between min and max. So one simple way, which is often done, consists in putting a penalty function, which is this red curve here, that says if the temperature is between the bounds, I pay nothing. If it's above, I pay for some penalty. If it's above or below. If I'm outside the band, I pay for something. It's called a soft constraint. What's the difference between a soft constraint and a hard constraint? Well, a soft constraint is soft. That means we will not guarantee that the temperature will always be exactly within this bounds. Our system will try very hard to make that true, but will not guarantee it. So it's less good from a modeling viewpoint. Why we do it is because it will be much, much easier to solve the problem. As we have painfully seen in the past 2 weeks, constraints in optimization problem leads to duality, Lagrange multiplier, all that kind of nasty things. So if we can remove them, that's the best. So we do it when the constraints are not hard. I mean, if we violate a bit the temperature, the world will not explode, right? If your temperature, if your set point is between, let's say this is the UK, so you say between 18 and 20, if your temperature gets 20.1 degree, there's no damage to the house or to the inhabitants. So it's the constraint in the nature of things is a desirable constraint, but not a hard constraint, right? So it's very appropriate in such cases to put a soft constraint. That's the red curve. Mathematically, the red curve, we can put it in this way. It's a max of 3 functions, which are linear, 0, that's the part in the middle. This one, which is t minus t max. And this one, which is minus t plus t min, which is this one here. So if we plot those 3 lines and we take the maximum, we obtain exactly this thing here. It's a convex function, which is piecewise linear. And a very frequent trick is to take piecewise linear convex functions because they can be expressed as the maximum of linear functions. It's linear with respect to capital T, my stated capital T. T min, T max are constant. The dependency that is important is with respect to capital T. So this is the background for our problem, how we have translated a problem of knowing when to heat the house into something that is now mathematically posed. Now, MPC. The trick of MPC is the following. We observe the current state. So MPC stands for Model Predictive Control. Model predictive in the sense that we know exactly the model and we can use the model to predict the result of taking a certain action if we know the disturbance here. So we observe the current state, and more precisely, we will predict the disturbance. That's the key stuff of the MPC. This form of MPC is called certainty equivalent MPC. We'll see another form in 1 hour of MPC. Certainty equivalent means we do a prediction for the future disturbance. Oops. Then we have a fixed horizon, h, number of times over which we do the prediction. For example, in the case of a house, that could be 1 or 2 days. We need to anticipate what happens in the coming 24 or 24 hours, for example. Then we solve an optimization problem that consists in saying if the uncertainties are exactly those predicted values, so no bad robust things to do like we had to do last week. We simply take those as certainty equivalent, that's the principle. And then we solve the optimization problem that consists in minimizing the cost from now until the end of the window, from now to the end of the next 24 hours. What is the trajectory of actions I should take? And given this, I implement only the first of those actions. And then the other actions I drop. They were just used for me to know what to do, but they're not implemented. Then time goes by and I can do a new observation. Nature will place the disturbance. The state will be perhaps not exactly what I had predicted because the prediction is never exact. There will be a new state that is given by nature and not entirely by me, and then I will do it again. So this is illustrated in this figure here. Model predictive control is used, for example, for driving cars autonomously. So any driver's assistance that is trying to automate driving a car is typically using model predictive control. And perhaps it's easier to visualize what model predictive control consists of. Assuming you are the software that has to take an action about driving the car, you have sensors that view, for example, the road and where you need to go. And Your goal is to go here, for example. So you solve an optimization problem that consists in, based on all the actions you can do, which are how you act with the steering wheel, how much gas you give, you compute a trajectory, an optimal trajectory that is constrained by the goals of being on the road here. Right? This is a temperature set band, if you want, but for a car it would be goal of being on the road. So you implement this, you think you would do this trajectory, but then perhaps there is some wind or some bumps on the road so that the trajectory is not exactly where you want it to be. Perhaps also there is inaccuracy in your model. We never, when we're engineers and we use MPC, we are never sure that we have 100% accuracy of the model. I mean, 100% accuracy of the physical world is very hard to get. So at time t plus 1, for a car that means perhaps 15 milliseconds later. For a house where we control the temperature, perhaps it means 15 minutes later, depends on the inertia of the system. So here, at time t plus 1, we will be here. So, and the difference is because of the disturbance that has been played by nature and all the random things that we could not forecast exactly. And at this point, you will compute a new trajectory. So this illustrates why it is good to have the complete trajectory, even if we implement only the first set point. If we are here, knowing the complete trajectory tells us we have to stay on the right here, so we have to turn right. And so why do we need to turn right? Because we know the road is turning right ahead of us, not just because of what we observe locally here. Right? So MPC always looks ahead in the future for deciding what to do at time t. That's the very strong thing of MPC. If you think about our house, we need to look ahead and have an idea what is likely to happen in many, many hours from now in order to decide whether to heat now or not. If we know the price of electricity will be very cheap in 1 hour, perhaps it's better to not heat now and let the temperature drop a bit and heat a bit later. So MPC always looks ahead in the future, but also, that's the second very important part, MPC adapts to the uncertainty. We have here a trajectory that has helped us decide to go here, but if at time t plus 1 we're not here, we'll do it again. So we'll compute a new trajectory. So this constant readaptation is what makes it very powerful. We say it's a receding horizon because the horizon we have is always moving on. At time t, we decide until this point. At time t plus 1, we will decide until another point here. So we have a sliding window of time that is moving ahead of us. So that's the idea. As you can see, it's fairly simple, but if we combine it with the ability that we have now to compute optimal solutions to optimization problems, that will give us something very powerful. So let's do it for David's house. I assume we have a prediction of the disturbance. So the disturbance is the outside temperature. So we need to have a prediction of the outside temperature. In fact, many heating systems have that. Simple predictions can be based on averages taken from the past years. Right? If we're in January, we know something of the temperature, which is likely to be different, even in the UK, of the temperature in August. Right? So we assume the temperature will be this. Of course, if we have more refined forecasts that we can get from a Swiss, Météo Suisse, for example, then we can even get better control. But even simpler predictions usually are useful, as we will see. And then we minimize the costs, which is in some sense an expected cost because they correspond to what we will have if the future temperatures are equal to the predictions. So that gives us this. We minimize over those animals, U and T. So those notation, that's MATLAB style notation. It means the range of all values of U from time t to t plus h minus 1. So the current value plus as many as we need to go to a horizon of length h. Also, we will, as a result of our control, there will be a temperature. So this temperature is not the true temperature, but this is the temperature we think will happen if the disturbance would be exactly equal to the prediction. And then we put in the constraints that we have for mass system. So this is the Planck equation, equality constraint. The temperature at time s plus 1 is given by this equation that we have discussed 5 minutes ago. And it will be true during my entire horizon. Then we have constraints on our heating system. Typically we have a max power. And if the max power in well-engineered heating systems, you don't want a max power that's too large because the heating system will be more expensive if the power is very large. But if the heating power is very small, we will have very little flexibility. So we might not be able to follow when it's very cold, for example. So that's a constraint on how much we can consume and therefore how much we generate. And the cost is the cost we gave before. That's the integral now in discrete time gives a sum of the price we will pay plus a penalty for violating the desired comfort zone. Here. So I repeat how such a system would work. At every time t, we observe the state, so we observe the house temperature. We compute the next actions that would be needed to be taken in order to minimize the cost, and we implement only the heating set point at time t, and then we do it again. So that's the problem we repeatedly solve. So with MPC, we need to solve a problem repeatedly, so hopefully the optimization problem doesn't take days of computation to be solved. So this is why we will be interested in linear systems. Here is an implementation and the result of what has happened. So we have here 2 days, and the horizon is 24 hours. The actual temperature is the blue dashed line here. So we see that there are, for some reason, some little changes here. The nice dashed black line is the temperature forecast, which is probably obtained from simply yearly averages. So that's what was forecasted here. The red y-axis here is the prices of electricity. We see that there are 3 prices: periods of low price, periods of high price, and period of intermediate prices. The low prices are at night here, and also at noon here. Why at noon? Probably because there is solar energy in this part of the grid. This is Cambridge. I said Oxford, I think I was wrong. This is Cambridge. In Cambridge, believe it or not, there's a lot of solar panels. And one of the effects of distributed energy resources, such as photovoltaic solar panels, is to change the prices of electricity. In fact, when the penetration of solar panels is very large, there is probably overproduction of electricity over noon, which is when there is maximum generation. The prices could be very different, of course, but this is the prices here. Now, on the top, we see the room temperature. I'm not showing the heat that is being used, but we can derive it from looking at the curve. We see the room temperature. The set band, the comfort zone is 19 to 21, which means we would like to be at 20 degrees here. And we see that, for example, at this point here, so if we would have a very, very powerful system, and we don't care about the price, then the room temperature should be close to 19 degrees. We allow anything between 19 and 21, probably the cheaper would be here. But here, that's not what the optimal solution does. The optimal solution, assuming it starts at 19 degrees here, will start heating. So here we heat the house. This is what the equations give. This gives this linear increase in temperature until we hit the maximum temperature, and then we stop heating. Since we stop heating, there's a decay, which is now like a negative exponential. The house is getting cold. Those are the laws of heat. The equations of heat will give something like this here. And then we heat again, and then the temperature drops again, and then we heat again, and we let it drop here. Now we can observe why we did that here. Here there is a price, there is a period of very high prices here, so we wanted to heat before, such that during this period of high prices, during this entire period of high prices, we don't have to heat. And here there's a small period of time around lunch, so we heat a bit more to take advantage of the low prices, and etc. Okay. So we see that the system is actually, because it knows the future prices, here I've treated the prices as deterministic, so they are hard-coded in the system. They could be taken as part of the disturbances as well. But here, since we know that electricity is, will be expensive here, we don't want to heat during this period. So I said something else. I said, no, here the price is expensive, so we heat in anticipation of a period where we don't want to heat. And since we're looking ahead, 24 hours, we're able to do that. Just like when we're driving the car and we see that the road is turning to the right, we're taking a right turn. This is what the system is doing. Now you see that the outside temperature is not following exactly the forecast, so of course that will impact also some of the system will react because it will sense the inside temperature. If the inside temperature in this case is decreasing less fast than it should because the outside temperature is warmer, then it will react and do perhaps less of its action. The cost here for 1 day or 2 days of operation is given here, 5.81, which we can compare to what thermostatic control would do. If you have simply a thermostat on your heating system, what does a thermostat do? A thermostat is trying to emulate the constant power, that would be the optimal one, but it cannot know exactly what the optimal is, so it will let the temperature drop, and then when the temperature gets below 19, in this example, it will heat until, so typically for a thermostat you don't have oscillations between as large as in the NPC that I saw below, so it will heat to get above and back into the comfort zone and then let it drop, and it does it myopically. So a thermostat is like an NPC that has only one step. It doesn't know the future. It sees I can let the temperature go down because the goal is to be above 19, not more. And as soon as I get below it, I heat until I go a bit above the threshold and then I stop. So we will have this typical saw-through behavior. Of course, the saw-through is a bit different here because this is the outside temperature being larger. So it's an approximation of a constant power. And the price here we see is almost 8 francs compared to the price of here, which is 5.8. That's the interest. We have been able to save on the money that we pay to the grid. That's the intention from the consumer viewpoint. Now, from a global smart grid viewpoint, what did we obtain by doing this? We also obtained that the consumer of this system has synchronized to a large extent the consumption of heat with the low prices. This is true here, this is true here. This is less true here, but that's the reason here it's forced to heat because the house is not perfectly insulated, the temperature would be too low. So it is forced to heat even though the price is high. But most of the time, it is consuming the energy when the price is low, which is one mechanism we have to orientate the consumption of the grid. Right? This is solving, I'm anticipating what we will discuss next week, but can you imagine why we would like to do this even more now than 50 years ago, perhaps? Well, if you think of this period here, when we have more renewable energies, they are random to a large extent. It may be sunny or not sunny. The wind may be strong or there may be no wind. So their production varies a lot. One way to handle this is to have reserves, gas-powered station that will compensate for the loss, such that we can follow exactly the load. But another way is to orientate the load to use more when it's available here. For example, if there's a lot of sunshine at noon, you would like that people use more of their energy at noon for heating the houses or for charging their car than at another point of the day. That's the topic of demand response that we will discuss in more detail next week. Those are the coefficients I took from David McKay's book. So the value of this book is to give, this is a physicist's book, so he's giving exactly all the quantitative values for everything, except here the violation, where I assumed here those amounts here. Questions so far? Okay. So, to use NPCs, we need to be able to manipulate them, and unfortunately, like for the rest of optimization, it's usually not sufficient to write to the NPC, use an NPC solver, and say solve it. It will be true if we can make it simple, and in particular, linear NPC. So what we will do is have to transform equations like we saw in the previous example to make them linear. This should sound familiar to us. We have seen a number of transformation rules for removing nonlinear systems. For example, here I'm showing a number of optimization problems. The first one is saying maximize epsilon over all epsilon in R, subject to epsilon being larger than some function of y for all y that satisfies some constraint. Same thing for minimize. And here another thing, maximal z over y is in some set, z is in R, and subject to this equality constraint, or maximize this function L of y over y in the set of constraints. Which of these problems are in fact equivalent rewritings? I close in 5 seconds. The majority says B, which is correct. So let's see why. First, there's something simple. C and D are the same. Right. Maximize Z over Y subject to Z here. So over y and z subject to z, right? And it's easy to see that we can remove the z is the same as maximize L of y over y. That seems obvious, but it's important to be able to do that kind of transformation. So C and D are the same. Now less obvious is that B is the same as that, right? So minimize epsilon over epsilon in R subject to epsilon larger than or than L of y. Well, we have no constraint on epsilon other than this one. So the given some y, the minimum of epsilon will be exactly L of y here. Or more precisely, this is what we have used many times, and we call it the max removal transformation, right? So I guess the important thing is to realize this, max removal transformation. If we have a problem of this kind, it's the same as that. In fact, we will use it. Going from B to C is perhaps not obvious, but it's not so difficult. But the trick we need to be able to master is going from C to B. When you have a function L that is not linear, then we may want to put it in this form, and then this will later be transformed here. More gymnastic about min and max. Here I'm showing two definitions of quantities A and B, A star and B star. I have a function of two variables, x and y. I take the max with respect to y, and then I take the min of the max. I call that A star. And I do the same by changing the order. The min is always over x, but I take it first. Does it matter? Does it make a difference? I close in 5 seconds. And the correct answer is certainly that they are not equal. And the correct answer is C. To see how, perhaps one simple thing to do is imagine that x and y are the indices of a matrix. So x is the index of a row in a matrix. Y is the index of the column. Right? In every cell of this arrow, you have a mouse or an elephant. Right? Or an elephant. And different mice have different weights, and the f is the weight, right? F of xy is the weight of the animal that's at coordinates xy. Now, some mice are lighter than some others, so different mice can have different weights, and same for elephants, but we assume that the heaviest mouse is lighter than the lightest elephant, which is probably true even at birth for elephants and at death from mice. So, if we look at this, then what is the first? Max, when we take the max first, and assume there is at least one mouse and one elephant on every row and every column. Sudoku style, we'll make sure there's always one mouse and one elephant on every column. Otherwise, it's random. So there are many possible choices, but assume this is true. If I take this, that means I take over one column the max weight. I will obtain the weight of the largest elephant. It certainly is an elephant. And it's the largest elephant here, on column here. Then I take the mean. Then I will have something which is the weight of the smallest weight of the heaviest elephant on a column. It doesn't really matter what it is certainly the weight of an elephant. Here. So A star is the weight of an elephant. When I take B star, what do? I take now a row, and on a row I take the smallest weight. Then it's the thinnest mouse. And then I take the max over all row. Again, it will be the weight of a mouse. So this will be the weight of a mouse. So the weight that is the largest of the mouse, that happens to be the largest among the smallest, but still it's a mouse. And here's the weight of an elephant. So B will be less than A star, at least in this case. And in general, it's true. And unless you're very lucky or there are strange things with elephant and mice, certainly B is going to be less than A in general, not equal. So the take-home message, mean and max, they should be taken care of carefully, right? The mean of the max is not the max of the mean. It's different. One typically leads to something much larger. If you take the max first and then the mean, you still have an elephant. If you take the mean first and then the max, you have a mouse. So they're not at all the same. Let's conclude before the break with this one. Now I have only means. Close in 5 seconds. Done. And then, of course, there is equality now. If you think of mice and elephants, what do we obtain when we do this? We take first the lightest on a column, the lightest mouse on the column. So it's the queen of this column, if being the queen is being lighter. And then we take the queen of the queens, which is the overall lighter mouse. It's the global mean, which we could have written also, the mean over x and y of f of x. And if we do it the other way around, we will of course obtain the same, because we obtain the winner, the mice that is the lightest among all mice. So this is what I was expressing here. If we take in this order, it's the same as taking the mean over all possible values seen globally here. This is called associativity of minimum. When we take the minimum of something in a big collection, we can group it as we want in the order. So the same is true for max, but as we've seen, not if we combine mean and max in the same expression. Voila, we'll do a break and we will see how this can be used to simplify our MPC formulation after the break. So we resume at 10:15.